There are planets in the Milky Way that never see a sunrise. They do not circle a parent star. No familiar sun climbs above their horizons. And no year is measured by a return through the same path of light. They move through the galaxy on their own, carrying whatever remains of their formation into the wide spaces between stellar systems. Astronomers usually call them free-floating planets. The more familiar name is rogue planets, though there is nothing unruly about their motion. Gravity still guides them. They orbit the center of the galaxy as stars do, passing through the same broad spiral structure as everything else in the Milky Way. What they lack is not direction but a nearby sun. A world like this may once have belonged to a planetary system. It may have formed inside a disk of gas and dust among other young planets before a close gravitational encounter changed its path. A larger neighbor could have pulled it into an unstable orbit. A passing star could have disturbed the entire system. Over time, one final encounter might have given the smaller world enough speed to escape. Other wandering objects may have formed in a different way from collapsing clouds that were too small to become true stars. The boundary between a planet and a failed star can become difficult to draw when there is no parent system to reveal how the object began. Mass can be measured only imperfectly. Origin is often hidden. Even the word planet begins to depend on a history that no telescope directly witnessed. After separation, the surface would lose the warmth of its star. Atmospheres could freeze, thin, or change chemistry. Ice might spread across oceans and rock. Yet the planet would not become physically inactive all at once. Heat left from formation, the decay of radioactive elements, and perhaps the pull of surviving moons could continue working below the surface long after starlight disappeared. These worlds are difficult to find because planets usually announce themselves through their stars. A planet may dim a star as it passes in front of it, or pull the star slightly back and forth through gravity. A rogue planet offers neither pattern. It produces no regular transit, no repeating stellar wobble, and often gives off too little heat to be seen across interstellar distances. For a brief time, however, its gravity can reveal it. When a wandering planet passes almost exactly between Earth and a distant star, its gravity bends and concentrates some of that star's light. The background star brightens for a short interval, not because the star itself has changed, but because space around the unseen planet has acted like a lens. The event may last only hours or days. Then the alignment ends, the star returns to normal, and the planet continues on. In this way, a world with no light of its own can leave a temporary signature made from someone else's light. The number of such planets remains uncertain. Small ones are especially hard to detect, and some candidates may actually travel in very wide orbits around stars too distant to notice. Yet observations and models both suggest that planetary systems can lose worlds and that the galaxy may contain a substantial population of these unattached travelers. Tonight, the journey follows one of them from its possible birth near a young star through the gravitational encounter that sends it away and onward into an existence measured across billions of years. It is not a story about a planet leaving the universe behind. It is a story about a planet. How much of the universe lies between the stars? A rogue planet begins in a place filled with light. Before it becomes a solitary world, it may form inside a young planetary system, surrounded by gas, dust, fragments of rock, and the bright turbulence of a newborn star. The star itself is still settling. Its light rises through a disk that stretches far beyond it, broad and thin, rotating like a vast wheel whose material has not yet decided what it will become. Within that disk, grains of dust collide. At first, the collisions are small enough to escape attention. Particles cling through surface forces. Clusters grow into pebbles, then larger bodies, each one moving through a crowded region where every orbit crosses the influence of something else. Some fragments shatter, others combine. Over time, gravity begins to matter more than contact. The largest bodies draw in nearby material and become planetary embryos. They do not occupy a finished solar system. They move through a changing environment filled with rival objects, shifting gas, and repeated encounters. The orderly arrangement we see in mature systems is the result of a long process that often begins in confusion. A young system may create more large bodies than it can keep. This is one of the simplest paths toward a wandering planet. Several growing worlds can form close enough together that their gravitational pulls overlap. Their orbits may appear stable for a while, perhaps for millions of years, while the disk around them gradually thins. Gas can soften some of their motion, drawing them toward more regular paths. But when much of that gas disappears, the planets are left to negotiate their positions through gravity alone. The negotiations are not conscious, of course, and they are not sudden in the way a collision appears sudden. They unfold through repeated tugs. One planet passes another and alters its speed by a small amount. A later encounter changes the angle of its orbit. The system continues through thousands of revolutions, carrying those changes forward until the geometry no longer closes neatly. Then two worlds approach too closely. Each one falls into the other's gravitational field. They do not need to collide. A close passage can exchange energy between them, leaving one planet on a tighter orbit and the other on a wider one. In the language of orbital mechanics, energy and momentum are redistributed. In the experience of the smaller world, its entire future changes during a passage that may last only a few days. If the outward moving planet gains enough speed, the star can no longer hold it. There is a threshold called escape velocity. It is not one fixed speed for an entire system, because it depends on distance from the star. Farther out, the star's grip is weaker. A planet already traveling through the outer regions may need only a modest additional push to enter an open path, one that does not curve back. The final encounter may involve a giant planet. Large planets are powerful sculptors of young systems. Their gravity can clear gaps, redirect smaller bodies, drive comets inward, and scatter planets outward. A world the size of Earth passing near a planet like Jupiter would feel a force strong enough to alter its orbit dramatically. Depending on the direction of approach, the smaller world could lose energy and fall inward, or gain energy and be sent away. The giant planet changes too, though, by much less. Momentum is shared. The difference is that the larger body is difficult to move, while the smaller one may be redirected across the entire system. A nearly invisible adjustment in the giant planet's orbit can correspond to exile for its neighbor. Not every ejection happens near one star. Some stars are born in groups. Young stellar clusters can contain hundreds or thousands of stars moving through the same general region before the cluster spreads apart. In such an environment, neighboring stars may pass close enough to disturb the outer parts of one another's planetary systems. A planet far from its parent star is especially vulnerable. Its orbit is wide, its motion is comparatively slow, and the binding energy that keeps it attached is low. A passing star does not need to come near the planet itself. It only needs to change the gravitational balance. The parent star moves one way, the planet another, and the relationship between them may not survive. Binary stars add another layer. A planet forming in a system with two suns can occupy a stable path, but only within certain regions. It may circle star while remaining far from the other, or orbit both at a greater distance. Between those stable zones are paths where competing gravitational pulls can accumulate into instability. A planet that migrates into the wrong region may be scattered, exchanged between the stars, or thrown beyond them both. Even a system that appears calm today may carry evidence of an earlier rearrangement. The planets around our own sun preserve traces of migration, collision, and scattering. The present architecture is not a photograph of the beginning. It is what remained after the unstable combinations disappeared. Some bodies struck one another, some fell into the sun, some were redirected to distant reservoirs, and some may have left the solar system entirely. This means a rogue planet is not necessarily a failed planet. It may have formed successfully, gathered an atmosphere, built layers of rock and metal, and perhaps collected moons. It may have spent millions of years under a young sun before one sequence of gravitational encounters removed it. Its isolation would not erase that earlier history. The materials of the original system would remain inside it. Iron could still rest in its core. Silicate rock could still form its mantle. Water, carbon compounds, and frozen gases might still lie within or upon it. A moon, if bound closely enough, might travel with it. The world would leave not as an empty stone, but as a complete record of the place where it began. The departure itself would not look like a dramatic launch. There would be no boundary marking the edge of the system. The parent star would simply grow smaller over time. Its disk, if any remained, would fade behind. Other planets would become faint moving points, then vanish into the glare of distance. The rogue world would cross the outer cometary regions and continue into interstellar space, still following the path gravity had given it. For a long while, the lost sun might remain the brightest object in its sky. Then even that distinction would disappear. The planet would enter the galaxy as one traveler among many, carrying heat, motion, and memory into the space between stars. There is no single moment when the planet becomes truly alone. Long after its last close encounter, the old star still remains behind it as a bright point. Its gravity continues to weaken with distance, but the light takes longer to fade. For a time, the planet moves through the outer edges of the system beneath a sky that still contains the sun of its birth. The change begins as a decline in energy. Every planet receives warmth from within and from outside. In a familiar planetary system, starlight heats the surface, drives weather, powers many chemical cycles, and sets the upper layers of the atmosphere in motion. Once a planet is thrown outward, that external source falls away according to a simple rule. Double the distance from the star, and the same light is spread across 4 times the area. At 10 times the distance, the planet receives only 1/100th as much. The cooling would not be immediate. Rock, ocean, ice, and atmosphere all store heat. A thick atmosphere could delay the loss by trapping infrared radiation. Deep oceans would release warmth more gradually than bare stone. The interior would continue supplying energy through radioactive decay and the slow release of heat left from formation. But the surface would begin to notice the growing distance first. If the world once had open oceans, ice would spread from the poles and across the continents. Weather systems would weaken as sunlight diminished. Clouds might thin, change altitude, or vanish depending on the atmosphere's composition. Photosynthesis, if it had ever developed, would lose its energy source. The familiar division between day and night would become less important as both sides of the planet cooled toward the same darkness. The atmosphere itself could begin to transform. On Earth, nitrogen and oxygen remain gases because surface temperatures keep them above their condensation points. On a wandering world, some gases could eventually freeze and settle onto the ground. Carbon dioxide might fall as snow. Methane could condense into frost or liquid. With enough cooling, even nitrogen could become part of the surface rather than the sky. This would not happen in the same way on every planet. A massive world can hold an atmosphere more tightly. A hydrogen-rich atmosphere can remain thick and insulating at temperatures that would collapse a thinner, heavier atmosphere. A small rocky planet may lose much of its gas over time, while a larger world may carry a deep envelope of hydrogen and helium into interstellar space. The difference matters because hydrogen is an effective keeper of heat under the right conditions. A planet with a dense hydrogen atmosphere could trap energy rising from its interior. Collisions between hydrogen molecules can temporarily create weak electrical imbalances, allowing the gas to absorb infrared radiation that would otherwise escape. This process, called collision-induced absorption, can produce a greenhouse effect even without sunlight. Models have shown that a sufficiently massive atmosphere might keep parts of a rogue planet warm enough for liquid water at the surface, at least under some combinations of mass, pressure, and internal heat. This is not evidence that such a world has been found. It is a physically plausible possibility, and one that depends on conditions we cannot yet measure for most free-floating planets. A less massive atmosphere would provide less protection. In that case, the surface might freeze completely while heat remained below. Ice is not only a sign of cold, it is also an insulator. As an ocean freezes from the top, the ice layer slows the escape of heat from the water beneath it. On Earth, this allows lakes to remain liquid below their frozen surfaces through winter. On a planetary scale, the same principle can operate for far longer. If radioactive elements continue warming the rocky interior, and if the ice shell grows thick enough to reduce heat loss, a buried ocean may survive after the surface has become rigid. The amount of internal energy depends on the planet's age, composition, and size. Large rocky worlds cool more slowly because they contain more heat and have less surface area relative to their volume. A young rogue planet may still be warm from formation. An older one may rely more heavily on radioactive decay in its mantle and crust. Moons could add another source. If a wandering planet carries a moon in an eccentric orbit, the changing gravitational pull could stretch and compress the moon's interior. This tidal flexing converts orbital energy into heat. The effect warms several moons in our own solar system, including worlds far from the Sun. A similar process could continue around a rogue giant planet, especially if multiple moons keep one another's orbits from becoming perfectly circular. The planet itself might also feel tidal heating if it retained a large companion. Two bodies do not need a star in order to exchange gravitational energy. They need only mass, motion, and an orbit that allows repeated flexing. From the surface, none of this heat would resemble daylight. It might appear as geothermal activity beneath the crust, as slowly circulating water below ice, or as chemical energy released where rock and water meet. Volcanic regions could remain active. Hydrothermal systems might continue along the floor of a buried ocean. The world above them could be frozen and black, while the interior remained dynamic. This changes the meaning of habitability. Around a star, the usual discussion begins with the habitable zone, the range of distances where a planet might maintain liquid water on its surface. A rogue planet has no permanent place in such a zone, yet liquid water does not require direct starlight if another energy source can keep it from freezing. Habitability is not the same as life, and neither is the same as evidence. A buried ocean may be chemically poor. It may lack the necessary ingredients, energy gradients, or long-term stability. It may never produce biology at all, but the possibility widens the range of environments in which liquid water could exist. A world may lose its sun without losing every path to warmth. Far above the frozen surface, the sky would change as the planet moved farther into interstellar space. The original star would join the rest of the stellar background. Familiar constellations would distort only very gradually, because the nearest stars are separated by such large distances. From most locations between systems, the Milky Way would still cross the sky as a broad band of accumulated starlight. The view would not be empty. Interstellar space contains gas, dust, magnetic fields, cosmic rays, and light from every direction. The cosmic microwave background passes through it. Starlight from the galaxy continues to arrive. Occasional high-energy particles strike the atmosphere or surface. The planet travels through a medium that is sparse by terrestrial standards, but never perfectly vacant. Its motion may carry it through different regions over millions of years. It could pass through a thin cloud of interstellar gas. It might move above or below the main plane of the galaxy, drift near a stellar nursery, or cross an older population of stars. Most of these passages would be distant and uneventful. Stars are so widely separated that a rogue planet can travel for immense spans of time without coming close to one. A new capture is possible, but unlikely. To become bound to another star, the planet must lose enough energy during an encounter. A two-body passage usually cannot do this. The planet falls toward the star, speeds up, swings around it, and departs with nearly the same energy it had before. Capture becomes more likely when a third body is involved, such as a second star or a planet already in orbit. Even then, the geometry must be favorable, so the first ejection may define the planet's future for billions of years. It will continue orbiting the center of the Milky Way, completing one galactic circuit over hundreds of millions of years. During that time, continents may stop moving or continue beneath ice. A magnetic field may weaken as the interior cools. Atmosphere may freeze, escape, or remain as a deep blanket. Moons may migrate. Buried water may persist, or eventually become solid from surface to sea floor. No observer has watched this full transformation. Astronomers reconstruct it through physics, computer models, planetary comparisons, and the faint traces of objects too distant to resolve clearly. Much remains uncertain because a rogue planet hides its history well. Its surface may reveal little about the system it left. Its atmosphere may be difficult to measure. Its orbit around the galaxy does not point backward to one recognizable star. Yet, the process itself follows familiar rules. Heat moves from warmer regions to colder ones. Gravity reshapes motion. Atmospheres respond to temperature and mass. Ice slows the escape of energy. Radioactive elements decay at measurable rates. The same physics that works beneath your feet also works on a world moving between suns. And while that world cools in the dark, its interior continues to spend the heat of an earlier time. A wandering planet does not usually reveal itself by shining. Most of the light in a planetary system comes from the star. Remove that star, and the planet becomes a small, cold body crossing a galaxy filled with brighter things. Even a world larger than Jupiter may be difficult to separate from the background once it has cooled for billions of years. A rocky planet can disappear almost completely into the distance. So astronomers often search for something the planet does rather than something the planet emits. Gravity provides the clearest signal. Every object with mass changes the geometry around it. A star changes it strongly. A planet changes it by less, but not by nothing. When a free-floating planet passes between Earth and a far more distant star, the planet's gravity bends the path of the arriving light. The alignment does not need to be perfect, though it must be very close. Light passing on different sides of the planet follows slightly different paths around the curved region of space. From Earth, those paths can combine into an image that is brighter than the background star would normally appear. The planet remains unseen. The distant star brightens. This is gravitational microlensing. The word lens is useful, but the planet is not focusing light through glass. It is altering the routes available to the light as it moves through space. The result depends on the mass of the lensing object, the distances between observer, lens, and source, and the speed with which the alignment changes. For a star, a microlensing event may last for weeks or months. For a planet, the event can be far shorter. A Jupiter-mass object may brighten a background star for days. A world closer to Earth in mass may produce a signal lasting only hours. Small planets leave brief marks, and the sky does not repeat them on command. This makes the search a form of patient attention. Astronomers monitor dense fields of stars, often toward the central regions of the Milky Way, where millions of possible background sources appear close together on the sky. Cameras take one exposure after another. Computers compare the brightness of each star through time, searching for the smooth rise and fall expected when a lens crosses the line of sight. Most stars do not change in the right way. Some flare, some pulse, some are eclipsed by companions. Detectors add noise. Earth's atmosphere adds its own motion and distortion. A useful survey must separate all of these patterns from the simple, temporary curve produced by gravitational lensing. A classic single lens event has a balanced shape. The star brightens as the alignment improves, reaches a peak, and fades as the lens moves away. The rise and fall are governed by geometry rather than by activity within the star. Observations made in different colors can help, because lensing brightens the source without changing its intrinsic color, in the same way many stellar variations do. Yet a short event does not immediately reveal a planet's full identity. The duration carries information about mass, but mass is not the only factor. A lighter nearby object can sometimes create a timescale similar to that of a heavier, more distant one. Relative speed also matters. Without additional measurements, several combinations can fit the same brief brightening. This is one of the central difficulties in the study of rogue planets. Astronomers may detect an isolated lensing event and infer that the lens probably has planetary mass. But the exact mass may remain uncertain, its distance may be uncertain, and the absence of an obvious host star does not prove that no host exists. The planet could be bound to a star in an orbit so wide that the star's lensing influence does not appear during the event. It might belong to a system whose host is too faint, too far away, or too close to the crowded background to identify immediately. A candidate can therefore occupy an uncertain category, either freely floating or traveling around a distant star on a very wide path. Follow-up observations can narrow the possibilities. Years after the event, the foreground lens and the background source may move far enough apart on the sky for powerful telescopes to examine the region more closely. If a host star is present, its light might eventually become distinguishable. If no host is found, some possible stellar companions can be ruled out, though extremely faint or widely separated hosts may remain beyond reach. Observations from more than one location can provide another piece of the puzzle. Two widely separated observatories do not view the alignment from exactly the same angle. A lensing event recorded from Earth and from a spacecraft may peak at slightly different times or reach slightly different magnifications. This parallax can help determine the scale of the lensing geometry. Combined with another measurement called the angular Einstein radius, it can sometimes allow the lens mass and distance to be estimated directly. The Einstein radius is not the physical edge of an object, it is a scale created by the lensing arrangement. Projected on the sky, it describes the region over which the gravity of the lens noticeably redirects the source light. For a planet, that region is so small that the multiple images it creates are usually too close together to resolve. Telescopes record their combined brightness instead. Sometimes, the background star itself has a measurable size in the event. If the lens passes across the face of the source, as seen from Earth, the star cannot be treated as a single point of light. Different parts of its disk are magnified by different amounts. This finite source effect changes the shape of the light curve, and that change can reveal the angular scale of the lensing region. A few events provide several of these clues at once. Most do not. That is why a population can become scientifically meaningful, even when individual objects remain partly unknown. One short event may not tell astronomers everything about one planet. Hundreds or thousands of events can reveal how common different masses are, how the population is distributed through the galaxy, and whether planetary systems eject small worlds as readily as large ones. The census is still incomplete. Early searches were most sensitive to objects near the mass of Jupiter. Later surveys with faster observing rhythms and more precise cameras began to find candidates with much shorter timescales. These signals suggest that the wandering population may extend into the range of Neptune, Earth, and perhaps below, though the abundance at each mass remains a subject of active measurement. The challenge grows as mass falls. A low-mass planet creates a smaller lensing region and a shorter event. If a survey checks the field too slowly, the brightening may occur between exposures. If the source star is large compared with the lensing scale, the signal can be spread out and weakened. Clouds, daylight, weather, and the rotation of Earth can interrupt a ground-based sequence at exactly the wrong time. Astronomers respond by building networks. Telescopes placed at different longitudes can hand the same star field from one night to the next as Earth turns. A field setting over one observatory may still be rising above another. Repeated images from sites in the southern hemisphere allow dense regions of the Milky Way to be watched with fewer gaps. Space changes the conditions again. Above the atmosphere, stars remain sharper, and measurements can continue without clouds or daytime sky at the observing site. A wide-field space telescope can follow enormous numbers of stars with stable instruments and a regular cadence. NASA's Nancy Grace Roman Space Telescope is designed to use this approach in a major survey of the galactic bulge, where microlensing events are frequent enough to build a far larger sample of planets. Roman's survey is expected to detect planets in ordinary orbits, as well as bodies that appear to travel without stars. Its sensitivity should reach far below the gas giants that dominated earlier searches. The importance is not only the discovery of individual worlds, it is the possibility of measuring the shape of the entire free-floating population. That shape can preserve the history of planetary systems. If giant rogue planets are common, while smaller ones are rare, one set of formation and scattering processes may be favored. If Earth mass wanderers greatly outnumber Jupiter mass wanderers, another history becomes more likely. The distribution can show how efficiently young systems produce planets, how often their orbits become unstable, and which kinds of worlds are most easily expelled. Microlensing is not the only method. Young, massive free-floating objects still release heat left from their formation. In infrared light, some can be seen directly, especially in nearby star-forming regions and young clusters. These objects may have clouds, weather, and spectra that reveal molecules in their atmospheres. Because they are young, they are warmer and brighter than older wanderers of the same mass. Direct imaging has its own uncertainty. A faint object seen by itself may have planetary mass, but its origin may resemble the formation of a very small star. Without a parent star, mass and history become entangled. An object below the conventional boundary for sustained deuterium fusion may be called planetary mass, yet that description does not establish whether it formed in a disk and was ejected or condensed directly from a cloud. Age also matters. A young low-mass object can resemble an older, heavier one because both may have similar temperatures and brightness. Astronomers use spectra, motion, association with nearby stellar groups, and models of cooling to estimate what it is. Every estimate carries a range. The two methods therefore see different parts of the hidden population. Infrared surveys are drawn toward young, warm, often massive objects. Microlensing can detect old and cold bodies because gravity does not fade as they cool. A planet that gives off almost no detectable light can still bend the light of a distant star. For the listener resting beneath an ordinary night sky, none of these events would be visible to the unaided eye. The brightening is usually too small, the star too faint, and the duration too brief. Yet observatories keep watch across thousands of nights, gathering small changes that would otherwise pass unnoticed. A planet crosses an unseen line. A distant star grows brighter. For a few hours, two objects separated by thousands of light years share one measurable geometry, and the wandering world leaves a trace before continuing beyond it. There is another layer beneath the frozen surface, one that cannot be seen even if the planet passes close enough for a telescope to detect it. A world moving between stars may look inactive from above. Its upper atmosphere could be thin or collapsed. Its plains may be covered by nitrogen frost, water ice, or compounds that would be gases under warmer conditions. But a planet is not heated only from the outside. Deep below, energy left from its formation continues to move outward through rock, metal, and ice. The earliest heat would have been immense. Growing planets are built through impacts, and each impact converts motion into warmth. Dense material sinks toward the center, releasing more energy as the interior separates into layers. Radioactive elements begin their long decay. Even after the planet has been expelled, these processes do not stop at the border of its former system. They fade according to their own clocks. A small rocky world loses internal warmth relatively quickly because it has a large surface area compared with its volume. A more massive planet stores more energy and releases it over a longer span. Composition matters as well. A mantle rich in radioactive elements can remain active longer than one, with fewer heat-producing isotopes. The exact history would depend on details no distant observer could easily recover. This hidden heat may decide whether water becomes one solid layer or separates into an icy shell above a liquid ocean. Near the surface, ordinary water ice can float because it is less dense than liquid water. That familiar property allows a frozen shell to form from the top downward. The ice then resists the escape of heat, and the deeper water remains insulated from the interstellar cold. Yet the interior of a large, water-rich planet would not resemble a lake beneath winter ice. Pressure rises with depth. Water molecules are forced into arrangements that do not occur at the surface of Earth. Several high-pressure forms of ice can appear even while the temperature remains high enough that ordinary ice would melt. These phases are solid, not because the planet is uniformly cold, but because the weight above them compresses the water into denser crystal structures. A deep ocean could therefore lie between two kinds of ice. Above it, a familiar low-pressure shell would face the surface. Below it, high-pressure ice might separate the liquid from the rocky mantle. The thickness of each layer would depend on planetary mass, water abundance, temperature, and the rate at which heat moves outward. That lower barrier is scientifically important. On Earth, seawater interacts with rock. At the ocean floor, chemical reactions exchange minerals and dissolved compounds. Hydrothermal systems create steep differences in temperature and chemistry. These gradients provide usable energy for ecosystems that do not depend directly on sunlight. If high-pressure ice isolates an ocean from the mantle, some of that exchange may be reduced. Nutrients could become harder to circulate. Chemical energy might be limited or distributed differently. The mere presence of liquid water would not guarantee an environment with the ingredients and imbalances that life could use. The opposite arrangement is also possible. A planet with less water, or with the right interior structure, may preserve contact between ocean and rock. Warm fluid could move through fractures in the seabed. Minerals could dissolve and reappear. Hydrogen might be produced when water reacts with certain rocks. carbon compounds could be carried between layers. None of this demonstrates biology, but it creates a more varied chemical environment than a sealed ocean alone. This is why the question of a hidden ocean cannot be answered with temperature alone. Liquid water is one condition. Long-term stability is another. Available chemistry, circulation, pressure, and sources of free energy all matter. A world can be warm enough for water, yet chemically quiet. Another can be colder overall, while maintaining active regions around faults, plumes, or hydrothermal vents. The planet's interior may also change slowly enough to create eras. During the first part of its wandering life, residual heat could support widespread melting beneath the shell. As billions of years pass, the ocean may contract. The icy boundaries could thicken from above and below. Pockets of liquid might remain near warm regions after the global ocean has diminished. Convection can delay this change. When warmer material rises and cooler material sinks, heat is transported more efficiently than by simple conduction. A rocky mantle may convect. Thick ice can convect as well, deforming over geological time, even when it appears rigid on human timescales. This movement could thin some regions of the shell and thicken others. It might create ridges, fractures, or broad resurfaced plains. A rogue planet with no sunlight could still have geology. Volcanism would be possible if enough internal melt remained. Cryovolcanism could carry water, ammonia, methane, or other volatile material upward through the ice. A plume might briefly place molecules from a buried ocean into the atmosphere before they froze and settled again. No such plume has been observed from a confirmed rocky rogue planet. The image belongs to physics and comparison, not to a known world. But similar processes within our own solar system show that distant, ice-covered bodies can remain active when internal energy is available. A companion moon could make the interior more complicated. During ejection, moons close to a giant planet may remain bound. Their orbits can be disturbed without being broken. If a surviving moon follows a slightly elongated path, the planet's gravity changes in strength across each orbit. The moon is stretched and relaxed again and again, and that repeated deformation produces heat. The same process operates on several moons near the outer planets of our solar system. Around a wandering giant, there would be no need for sunlight to maintain it. The energy would come from motion within the planet-moon system. For a time, tidal heating could be strong enough to support liquid water beneath ice, or under some modeled conditions, even at a moon's surface if a thick atmosphere retained the warmth. How long this lasts depends on the orbit. Tidal forces tend to make an orbit more circular, reducing the flexing that generates heat. Other moons can preserve eccentricity through gravitational resonances, extending the active period. So a single rogue planet might carry a small system of its own. There could be a giant world wrapped in hydrogen and helium, surrounded by moons that formed in a disk around it. Some moons might be rocky, others might contain large amounts of ice, rings and debris after the violence of ejection, though their survival would depend on how close the scattering encounter had been. From far away, the planet and its moons would appear as one faint source, if they were visible at all. Their internal arrangement could remain hidden from present instruments. Yet the system would continue running. Moons would orbit, tides would transfer energy. Magnetic fields might guide charged particles through the planet's surroundings. Auroras could occur without a nearby sun if plasma were available from a moon, an atmosphere, or the interstellar environment. A strong magnetic field would not warm the surface enough to replace starlight. It could, however, influence atmospheric loss and the movement of charged particles. Whether it protects an atmosphere depends on the planet, the field, and the surrounding plasma. Magnetic fields do not act as simple shields in every case. Cosmic rays would still reach the system. Without a star's wind and magnetic bubble, the planet would travel directly through the galactic environment. High-energy particles could enter its atmosphere and strike exposed ice. They might break molecules apart and allow new compounds to form. Most of this chemistry would occur near the surface, far above any deep ocean, but fractures, impacts, or slow recycling could move some products downward. The absence of sunlight therefore removes a major energy source without producing complete chemical stillness. There would be radioactivity in rock, pressure in deep water, motion in convecting layers, tidal friction in moons, and particle-driven reactions near the surface. Each source is limited. Each operates on a different scale. Together they create a planet that may be dark without being simple. The greatest uncertainty lies in how often all the necessary conditions overlap. A free-floating world would need the right mass, composition, water inventory, atmosphere, interior heat, and geological history. A moon would need to survive ejection and remain in an orbit that supplies useful tidal energy without becoming destructive. Liquid water would need to persist where chemistry can continue. Stability would need to last long enough for complex processes to unfold. Even then, there is no reason to assume life begins. Habitability describes conditions that might permit biology. It does not predict that biology must appear. On Earth, life is known to have emerged early, but we have only one inhabited planet from which to judge how likely that transition may be. A hidden ocean on a rogue planet would be difficult to test from across the galaxy. Its surface might reveal almost nothing. Atmospheric measurements could hint at internal chemistry, but many gases can have non-living origins. A brief microlensing event may tell us that the planet exists while leaving its layers, moons, and history unresolved. For now, these worlds occupy a region between observation and informed possibility. Gravity shows that unattached planets are real. Planetary physics shows that internal warmth can outlast the loss of a star. Studies of ice, atmospheres, tides, and radioactive decay describe ways liquid water might survive. The step from possible water to a living ocean remains open. Still, the idea changes the map. Warmth need not arrive from above. A habitable region need not be drawn as a ring around a sun. Some environments may be enclosed, powered from within, and carried through the galaxy beneath kilometers of ice. Beyond every visible constellation, there may be worlds whose most active landscapes have never known a sky. A rogue planet does not remain near the place where it was born. Once the gravity of its parent star releases it, the world joins the larger motion of the galaxy. It no longer circles one sun, but it still follows the combined pull of billions of stars, clouds of gas, stellar remnants, and dark matter spread through the Milky Way. Its path becomes a galactic orbit. The planet may travel in the same broad direction as nearby stars, moving around the galactic center at hundreds of thousands of kilometers per hour. That speed sounds immense, only from a stationary point of view. The surrounding stars are moving as well. Relative to them, the planet may pass through its local region at a more modest pace, as though it were carried within a vast rotating current. The orbit is not a perfect circle. Stars and planets move slightly inward and outward as they travel. They also rise above and fall below the thin central plane, where much of the galaxy's visible matter is concentrated. A wandering planet may spend part of its journey among crowded stellar regions and another part in areas where the nearest stars are several light years away. One circuit around the Milky Way can take hundreds of millions of years. During a single galactic year, continents could shift, oceans could freeze more deeply, moons could change their orbits, and entire species could appear and disappear on an inhabited planet elsewhere. The wandering world would continue through all of it, passing from one region of the galaxy to another without any nearby sunrise to divide the time. Its original star would gradually become impossible to identify. At first, the direction of departure might point back toward the system it left. But stars move. Gravitational encounters alter trajectories. The spiral arms are not rigid structures carrying the same stars forever. Over time, the planet and its former sun follow separate paths through the galactic disk. After millions or billions of years, even perfect knowledge of the planet's present motion might not be enough to reconstruct its birthplace. Small uncertainties grow when a trajectory is traced backward through a galaxy filled with moving masses. The world carries evidence of its origin in its composition, but its route home may be permanently lost. That hidden origin creates a challenge for classification. Imagine two dark objects with the same mass and temperature. One formed around a star, growing from a disk before being thrown into space. The other formed directly when a small cloud of gas collapsed under gravity, following a process more similar to the birth of a brown dwarf. Seen alone, they might look nearly identical. The first would be a planet by its history. The second might be described as a planetary mass, brown dwarf, a sub-brown dwarf, or simply a free-floating planetary mass object. The terminology remains unsettled because nature does not always preserve the boundaries used in catalogues. Mass offers one possible dividing line, but it is incomplete. Objects above a certain mass can briefly fuse deuterium, a heavy form of hydrogen, in their interiors. The approximate threshold is often placed near 13 times the mass of Jupiter, though the exact value depends on composition. This limit has sometimes been used to separate planets from brown dwarfs, but fusion does not reveal how an object formed. A body below that threshold can collapse directly from a cloud. A body above it could, in principle, form in a disk. The ability to burn deuterium describes an internal process, not a birth certificate. Formation is scientifically meaningful because it preserves different histories. A planet built in a disk may contain a larger fraction of heavy elements than its parent star. It may possess a core formed from rock and ice before gathering gas. Its atmosphere may show chemical traces of the disk region where it grew. A directly collapsed object may more closely resemble a very low-mass star in its overall composition and internal structure. These distinctions are difficult to measure from a faint point of infrared light. Young free-floating objects are the most accessible because they are still warm. Their interiors release energy left from contraction and formation, and this heat escapes through thick atmospheres filled with molecules, clouds, and weather. Some have temperatures comparable to hot ovens. Others are cool enough for water vapor, methane, ammonia, and complex clouds to influence their spectra. The coolest known examples approach temperatures found on parts of Earth, though they remain massive gaseous bodies rather than Earth-like worlds. Their atmospheres can behave in unfamiliar ways. Without a nearby star, there is no strong day side or night side. Heat rises from within and moves outward across the entire globe. Rotation organizes winds and storms. Clouds may form in layers made from silicate particles, iron droplets, salts, sulfides, or water, depending on temperature. A young planetary mass object can therefore resemble a world with endless weather and no sunlight. Changes in brightness as the object rotates may reveal uneven cloud cover. One region may be thicker or warmer than another. A storm system can move into view and then disappear. These variations allow astronomers to infer rotation periods and atmospheric patterns from objects that cannot yet be seen as resolved disks. As the world ages, the weather changes. The interior contracts and cools. Silicate and iron clouds sink below visible layers. Other compounds begin to condense. Methane becomes more prominent. At lower temperatures, water clouds may form. Given enough time, the object becomes fainter at infrared wavelengths and harder to discover. Cooling creates a selection effect. The rogue planets visible through direct imaging are usually young, nearby, or massive. Old Earth mass worlds may be far more common and almost entirely absent from infrared catalogues. Their temperatures could be so low that even large telescopes would struggle to distinguish them from the background. Microlensing does not share this preference. Gravity depends on mass, not warmth. An old planet can bend light as effectively as a young planet of the same mass. This makes microlensing valuable for building a census that includes worlds invisible to direct imaging. Yet microlensing events are brief and usually happen only once. The lens moves on. The background star returns to its normal brightness. In many cases, the planet itself is never photographed. Astronomers are left with a light curve, a measured timescale, and a range of possible masses and distances. Direct imaging offers atmospheric information but favors bright youth. Microlensing reaches darker and older objects, but often provides little detail about any one of them. Together, the methods begin to outline a population. That population may contain several overlapping groups. Giant planets expelled from mature systems, smaller worlds scattered during formation, bodies released when stars pass near one another, and planetary mass objects that formed alone. Each group should produce a different distribution of mass, speed, age, and chemical composition. The number of rogue planets can therefore test models of planetary formation. Computer simulations begin with young stars, surrounded by disks and growing worlds. Researchers allow gravity to act over millions or billions of simulated years. Planets migrate, orbits cross, giant worlds scatter smaller neighbors. Some objects collide, while others fall into the star or escape. The outcome depends strongly on the starting conditions. A tightly packed system is more likely to become unstable. Several giant planets can produce powerful scattering. The presence of a binary star changes the stable regions available. A dense birth cluster increases the chance of external disturbance. If surveys find many free-floating giant planets, planetary systems may produce and eject large worlds more efficiently than some models predict. If most rogues are small, instability may be especially effective at removing lower mass planets, while larger bodies remain. There may also be systems that lost nearly everything. A star observed today with one distant planet could once have held several. Another star with no detected planets might have formed a full system before gravitational encounters cleared it. The current arrangement of a mature system reveals only the survivors. Our own solar system may also have lost bodies during its early history. Models of the outer planets sometimes include additional ice giants that were later ejected as the giant planets changed orbits. This remains a theoretical reconstruction rather than an observed event, but it demonstrates how a system resembling ours could have produced a rogue world. If such an object left the solar system billions of years ago, it would now be far away. It might still orbit the Milky Way in a path broadly similar to the Sun's, yet the distance accumulated over time would place it beyond recognition. No visible mark would identify it as a former member of our planetary family. The thought does not require imagining a familiar world waiting nearby. It reveals something more general about planetary systems. Their finished shapes can conceal earlier losses. Stability is often what remains after instability has removed the alternatives. A wandering planet is one of those alternatives made physical. It is a world that did not collide, did not fall into its star, and did not settle into a lasting orbit. It received enough energy to cross the boundary between belonging and departure. From then on, close encounters with stars would be rare. Interstellar distances are large, and a planet is a small target. Most passages would occur many thousands of astronomical units away, producing only minor changes in direction. The world could complete several galactic orbits without entering another planetary system. A very close stellar passage could redirect it. A binary star might even capture it if the geometry allowed energy to be transferred between three bodies. The planet could emerge bound to one star, orbit both, or disturb planets already present. But capture is difficult, and a stable final orbit is harder still. Most rogue planets may remain rogue planets. Their journeys are not aimless. Each follows gravity with complete precision, even when its path cannot be traced to an origin or destination. They cross spiral arms, pass through interstellar clouds, rise above the galactic plane, and return. Around them, stars form and die, clusters dissolve. The shape of the Milky Way slowly changes, and through that changing galaxy, the planet carries one system's unfinished history into another age. Most wandering planets will never pass close to another star. The galaxy contains hundreds of billions of us, yet the spaces between them are so large that even a planet traveling for billions of years may cross those distances without entering a region we would recognize as a planetary system. Its path could carry it through spiral arms and stellar neighborhood, while leaving the nearest stars far beyond the orbit of any familiar planet. But rare encounters do occur. A rogue world may approach a star from interstellar space with a speed and direction shaped by its long galactic journey. At first, the star is only another point of light. Over thousands of years, it brightens. Its gravity begins to curve the planet's path, drawing the traveler inward along a broad arc. The planet does not fall straight toward the star. It arrives with sideways motion, and that motion matters. Gravity increases its speed as the distance closes, but the original direction carries it past the star unless something removes enough energy to prevent escape. In the simplest encounter, the planet swings around the system and departs again. This kind of passage is called a gravitational flyby. The star changes the planet's direction, sometimes by a large amount, while the planet exerts a much smaller pull in return. From a distant viewpoint, the trajectory resembles a curve with two open ends. The rogue, who enters from interstellar space, passes through the star's gravitational influence and leaves on a new path. Its brief visit could last for centuries. That may seem long, but planetary systems are wide. A traveler moving through the outer cometary regions may spend generations crossing distances that light covers in hours. Only the closest part of the encounter would unfold quickly by astronomical standards. If the system has planets of its own, the geometry becomes more complicated. A rogue world passing far outside the major planets may do little more than disturb distant comets. The outermost reservoirs of small icy bodies are held only weakly by their star. A passing planet could redirect some of them inward, push others farther away, or remove them from the system entirely. Closer passages could alter planetary orbits. The effect would depend on the intruder's mass, speed, and distance of approach. A low-mass planet moving quickly through the outer system might leave only subtle changes. A giant world passing near an established planet could exchange enough energy to reshape both paths. The encounter would not need to produce a collision. Gravity acts across distance. One planet might be driven inward toward the star. Another could be moved onto a wider, more eccentric orbit. In an unstable arrangement, a resident planet might be expelled, while the original rogue continued onward or remained behind. A system could exchange one world for another. This possibility appears in simulations of young clusters, where stars and planets pass more closely than they usually do in the settled galactic field. A free-floating planet may enter a system already containing planets, interact with one or more of them, and leave the encounter gravitationally bound to the star. Capture requires energy to be transferred. With only one star and one planet, a permanent capture is difficult. The planet speeds up as it falls inward and loses that extra speed as it moves away. Without another body or another mechanism, The incoming and outgoing energies remain nearly balanced. A third object can change that balance. The rogue planet may pass near a planet already orbiting the star. During the encounter, one body can carry away more energy while the other loses enough to remain bound. A binary star offers another route. The changing gravitational field of two moving stars can redistribute energy in ways a single stationary star cannot. The result may be a captured planet on an unusual orbit. It could travel far from the star, following a stretched ellipse that takes thousands of years to complete. Its orbital plane might be sharply tilted compared with the system's original planets. It might even move in the opposite direction. Such an orbit would preserve a clue to its arrival. Planets formed from the same disk usually begin with related orbital directions and inclinations. Later interactions can disturb them, but a distant world moving backward or far outside the main planetary plane may suggest a history involving scattering or capture. Suggestion is not proof. A planet can reach an unusual orbit through several processes. A companion star may tilt it. Interactions among native planets may send it outward. The original disk itself may have been warped. Astronomers must compare many possibilities before identifying capture as the best explanation. A captured rogue world would also carry a composition unrelated to its new star. It might have formed around a star richer or poorer in heavy elements. Its atmosphere could contain proportions of carbon, oxygen, and other elements that differ from those expected in the new system. If future telescopes can measure such atmospheres in detail, chemical mismatches may help reveal worlds that began elsewhere. The distinction would be difficult to establish. Planetary atmospheres change over time. Chemistry is influenced by temperature, mass, clouds, internal mixing, and the loss of gases to space. A chemical difference could reflect formation in another system or merely formation in another region of the same disk. Still, the possibility broadens the idea of a planetary family. Not every planet around a star must have been born there. Some systems may contain adopted worlds, acquired during the crowded early life of a stellar cluster. A planet could begin beside one sun, wander for a time, and later settle around another. Its sky would gain a new source of day, but the materials beneath that sky would belong to an older place. The arrival could transform the captured planet. If it had spent millions of years in darkness, approaching a star would warm its atmosphere and surface. Frozen gases might begin to sublimate. Nitrogen, methane, carbon dioxide, or water could return to the atmosphere, depending on the temperature reached. A frozen ocean would respond more gradually. The upper ice might absorb sunlight, while the deeper shell remained cold. Cracks could widen as temperatures changed. Volatile material trapped beneath the surface might escape through weakened regions. If the orbit were highly elongated, the planet could experience a short, warm interval near the star and a long, cold interval far away. Its climate might never settle. On each orbit, atmosphere could expand during the close passage and partially collapse again as the planet retreated. Winds could move newly released gases across the surface. Frost could migrate from one hemisphere to another. The planet would carry its interstellar past into a repeating cycle of warming and freezing. A captured moon system could face greater disruption. Moons that survived the original ejection might be stripped away when the planet entered the new star's gravitational field. The widest moons would be most vulnerable. Close companions could remain, but their orbits might be stretched or tilted. A moon removed from its planet could become a planet-like body orbiting the star on its own. The labels would change even though the object did not. A moon in one system could become a small independent world in another. Classification follows relationships, and relationships can be rearranged. Some encounters end more violently. A rogue planet passing too close to a star could be torn apart by tidal forces, especially if it approached within a few stellar radii. Its fragments might form a temporary stream or disk. Material could fall onto the star, adding elements that leave faint chemical traces in the stellar atmosphere. A direct collision with a star is possible, though the star occupies only a small part of the system's available space. A collision with another planet is also possible, but rare. The more common outcome is deflection. For most wanderers, counter changes direction and little else. The planet approaches, accelerates, and crosses a sky filled with a new sun. For a time, one hemisphere may receive light brighter than anything the world has known since its exile. Frozen compounds may respond at the surface. Clouds may form where none existed before. Then the planet moves away. The temporary sun becomes smaller. Any released atmosphere begins to cool. Refrozen gases settle across the ground. The warmth of passage leaves the surface, and the interior once again becomes the planet's most dependable source of energy. The flyby may add or remove moons. It may redirect the world toward a different region of the galaxy. It may leave no permanent change beyond a new trajectory. Even so, the planet has entered another system's history. Distant comets may follow altered paths. A resident world may acquire a slight eccentricity. Debris may be scattered into new orbits. Centuries later, observers around that star might detect these changes without ever seeing the object that caused them. A visitor can leave evidence after it is gone. The same is true in reverse. A rogue planet carries the marks of encounters that no longer have visible sources. Its orbit around the galaxy, its surviving moons, its atmosphere, and the distribution of heat within its layers may all contain traces of stars it once passed. No single mark would reveal the complete journey, but together they describe a world whose identity has shaped not only by the system that formed it, but by every gravitational field it has crossed since. Between the stars, even solitude is part of a larger exchange. A planet is often imagined through its relationship to a sun. It circles a star, it receives light. Its seasons, climate, and years are shaped by that orbit. Even the word planet entered human thought through the moving lights of our own sky, objects distinguished from the fixed stars. Because they wandered against the background, rogue planets reveal that wandering can continue on a much larger scale. They are not failed versions of familiar worlds. They are reminders that a planet can remain physically complete after the relationship that once defined it has ended. Gravity still rounds it, its interior still cools, its atmosphere still responds to pressure and temperature. Moons may still circle it. Chemistry continues within rock, ice, and gas. What disappears is the nearby reference point. Without a parent star, there is no obvious year. There may be rotation, and therefore a measurable day, but the passage of time would not be divided by seasons of light. A geological process could continue for millions of rotations without any sunrise marking its progress. For human observers, this absence makes the planet difficult to place. Most astronomical measurements depend on relationships. A planet's orbit reveals the mass of its star. Its temperature can be compared with the energy it receives. Its age may be estimated from the stellar system around it. Its composition can be understood partly through the disk from which it formed. A free-floating world removes many of those clues. Astronomers may see only a brief brightening of a distant star or a faint infrared point moving across several images. From that limited evidence, they try to recover mass, distance, temperature, motion, and age. Each measurement narrows the possibilities, but the planet's full story remains larger than the signal. This is not unusual in science. The universe rarely presents complete histories. It provides traces. Light arrives after a journey. Motion records the influence of gravity. Chemistry preserves earlier conditions imperfectly. Researchers build explanations by finding which physical histories could have produced the evidence that remains. A rogue planet is especially suited to this kind of reconstruction because its most important event may have happened billions of years ago. The ejection itself is gone. The encounter that caused it cannot be repeated. The other planets have moved on. The birth cluster may have dispersed until its stars are scattered across the galaxy. What survives is the world and whatever signatures it still carries. Its speed may suggest how strongly it was scattered. Its atmosphere may contain clues to where it formed in a disk. Its moons may indicate whether the departure was distant or close. Its internal heat may reveal something about its age and mass. None of these clues speaks alone. Together, they can place limits around a history that remains partly hidden. As surveys improve, the most important result may not be one unusual planet, but the shape of the entire population. A census of wandering worlds could reveal whether ejection is a rare accident or a common stage of planetary development. It could show whether small planets are scattered more often than large ones, whether giant worlds usually remain with their stars, and how strongly birth environments influence the systems that survive. The answer may change how we interpret ordinary planetary systems. A calm arrangement observed around an old star may be the residue of an earlier period filled with migration and loss. Widely separated planets may have settled only after other worlds were removed. A single surviving giant may have reached its present orbit by passing gravitational energy to bodies that are no longer there. In this sense, a rogue planet belongs to two histories. It belongs to its own continuing path through the Milky Way. It also belongs to the missing architecture of the system that released it. The planet is evidence of absence. That phrase can sound abstract, but the physics is direct. Momentum must be conserved. Energy must be exchanged. A world cannot be expelled without altering the bodies that remain. Somewhere, another planet may have moved inward. A giant may have shifted outward. A binary companion may have changed the balance of an entire young system. The wanderer carries one side of that exchange through interstellar space. There is a human habit of treating location as identity. Earth is the planet around the Sun at one astronomical unit. Mars is the colder neighbor beyond it. Jupiter is the giant that circles farther out. Their names are attached not only to their materials, but to their positions within a shared system. A rogue world makes that connection less secure. Move a planet beyond the boundary of its star, and its rock does not become less planetary. Its oceans, if they exist, do not lose their physical meaning. A moon does not stop orbiting because no sunlight reaches it. The world remains itself even when the map around it changes completely. The same is true of captured planets. A world may begin around one star, travel alone, later settle around another. Its new orbit would describe where it is, not where it came from. The light above its surface could belong to a sun that played no role in its formation. Future observations may uncover examples of such histories, though proving capture will be difficult. Unusual orbits, chemical differences, and dynamical models may point toward an outside origin. Even then, several explanations remain possible. Uncertainty is not an empty space in the knowledge. It has structure. Astronomers can say which masses are allowed, which orbits are stable, which atmospheres could retain heat, and which formation paths fit the evidence. A good scientific description does not pretend that one possibility is certain when several remain. It maps the boundaries between what has been measured, what follows from physics, and what still waits for evidence. Rogue planets inhabit those boundaries naturally. Some are detected through gravity, but never seen directly. Some are seen in infrared light, but have uncertain origins. Some may be planets expelled from disks. Others may be low-mass objects formed more like stars. The The categories overlap because the universe is continuous where human language prefers divisions. The distinction still matters because formation shapes composition, structure, and population, but the uncertainty does not make the objects less real. It reveals that a single label may not capture every route by which a world can exist. There may be enormous numbers of these objects in the Milky Way, but their abundance remains difficult to measure. Large rogue planets are easier to detect in some surveys. Small ones produce shorter lensing events. Old ones are faint, wide. Orbit planets can imitate isolated worlds if their stars are too distant from the event to leave a visible signal. Every census must account for what the instruments are likely to miss. This is why a few detections cannot immediately describe the whole population. Researchers model the survey itself, how often it observed, which stars it monitored, what event durations it could recognize, and how noise affected the result. Only then can observed events be translated into an estimate of what may exist unseen. The invisible majority is inferred from the visible fraction. That method appears across astronomy. Telescopes detect the light that reaches them, while statistical models describe the objects that did not happen to align, brighten, transit, or remain warm enough to observe. A rogue planet may cross the galaxy for billions of years without lensing a star from Earth's point of view. Its existence does not depend on being detected. The event depends on geometry, and geometry is rare for a listener beneath the night sky. This creates an unusual perspective. The spaces between visible stars may contain complete worlds that contribute almost no light to the scene. They may pass through the same galactic neighborhood as the Sun, while remaining too far away and too cold to notice. The sky can appear empty where it is only unilluminated. That does not mean a rogue planet is likely to be nearby, or that one is passing through the solar system now. Interstellar space is wide, and known candidates are distant. The idea is not one of hidden visitors surrounding Earth. It is a change in scale. A galaxy is not composed only of what shines. It contains cooled remnants, dust, gas, dark matter, small bodies, and planets without suns. Visible starlight traces only part of the structure. Long before telescopes could detect such worlds, people used the planets above them as reliable moving lights. Their paths could be followed from night to night because the Sun held them in repeated orbits. Now astronomy has extended the old meaning of wandering beyond the visible sky. Some worlds move without returning to the same stellar path. They cross regions no human observer has named. Their days continue without dawn, and their histories unfold without anyone present to divide them into chapters. Yet they remain within the same galaxy. The gravity guiding them also guides the Sun. The elements inside them were made through the same stellar processes that produced the materials of Earth. Their heat moves according to the same laws. Their ice, rock, atmosphere, and motion are not foreign to nature here. They are distant expressions of familiar physics, and perhaps that is what makes them feel less like lost worlds than worlds whose paths are simply longer than the systems that first held them. Eventually, every journey through the galaxy becomes a journey through time. A rogue planet may continue long after the system that formed. It has changed beyond recognition. Its parent star may grow older, brighten, expand, and shed its outer layers. Neighboring stars may be born from clouds that did not exist when the planet was expelled. The spiral pattern of the Milky Way may shift around it, while the world completes one galactic orbit after another. The planet does not stand outside these changes. Its own interior cools. Radioactive elements become less abundant. Geological motion weakens. A magnetic field may fade as the core loses energy. Moons move gradually through tidal interactions, drawing closer or farther away, depending on the direction of rotation and orbit. A buried ocean, if one exists, may survive for a long time. Ice above it slows the loss of heat. Rock below it may continue releasing energy. Tidal motion may keep some regions warmer than others. Yet no internal source lasts forever at the same strength. Over immense spans of time, the liquid layer could become thinner. High-pressure ice may rise from below. The upper shell may grow downward. Circulation may slow as the remaining ocean becomes enclosed between colder boundaries. Chemical exchange with the rocky interior may diminish. The world would not freeze in a single event. It would pass through stages. A global ocean might become several connected basins. Those basins could separate into isolated reservoirs. The last liquid regions may remain near warm fractures, deep mantle boundaries, or tidally active zones. Eventually, even those places may become still. For a gas giant, the ending would be different. A massive hydrogen-rich rogue planet would cool and contract over billions of years. Its atmosphere would remain deep, though the visible cloud layers would change as temperature fell. Compounds that once existed as gases would condense, storms would weaken or move deeper into the atmosphere. The planet would continue releasing heat, but less with every age. From far away, its infrared glow would fade until it became difficult to distinguish from the cold background of space. Gravity would remain unchanged enough to bend the light of a distant star, but the planet's own radiation would carry less information to any observer searching for it. A rocky world would become darker still. Its atmosphere might lie frozen across the surface. Ice would cover impact basins, plains, and old mountains. Without erosion driven by rain, rivers, or active weather, some features could remain for enormous periods. Occasional impacts would continue. Interstellar space contains small bodies as well as planets. A wandering world may be struck by dust, rock, or ice during its long orbit around the galaxy. Most impacts would be minor. A large collision would be rare. But given enough time, rare events remain possible. An impact could briefly warm part of the surface. It might melt ice, release frozen gases, or expose deeper material. A temporary atmosphere could spread around the planet before cooling and falling back to the ground. Beneath the impact site, liquid water might survive for a time and then freeze again. The planet would return to its older condition. Encounters with stars would also remain possible, though widely separated. One could redirect the planet's orbit around the galaxy. Another might warm its surface for a short passage. A rare capture could give it a new sun. Most journeys would contain no such change. The world would continue through the spaces between stellar systems, completing its path under the combined gravity of the Milky Way. Far in the future, the galaxy itself will not remain as it is now. Stars exhaust their fuel. New star formation becomes more difficult as usable gas is consumed or dispersed. Bright regions fade. Long-lived red dwarfs continue shining after larger stars have disappeared. Stellar remnants accumulate. A rogue planet may survive through much of this transition. It requires no parent star to maintain its orbit around the galaxy. It does not depend on one system remaining stable. As stars evolve, the planet continues through the changing gravitational landscape. Its path may be altered when stars lose mass. A star shedding material weakens its gravitational influence. Objects that once orbited far from it can escape. More planets may become free-floating as their suns age, adding later generations of wandering worlds to those expelled during planetary formation. The galaxy may therefore produce rogues at more than one stage. Some leave young systems through instability. Some are released from wide orbits when passing stars disturb them. Some may be set free when aging stars lose enough mass that distant planets are no longer securely bound. Each world enters interstellar space with a different history. A young rogue can carry formation heat and an active atmosphere. An older planet, released late, may already contain a long geological record shaped by billions of years of sunlight. It could leave its star only after oceans have vanished, moons have moved, and continents have changed many times. The word rogue gathers all of these histories into one category, but the category contains many kinds of worlds. Some may be giant and warm enough to detect in infrared light. Some may be smaller than Earth and almost impossible to find. Some may have moons. Some may carry thick atmospheres. Some may be frozen to the core. Others may preserve liquid layers far below their surfaces. Most will never align with a background star from our viewpoint. Most will never pass close enough to emit a measurable signal. Their number may be large, yet each detection depends on a narrow arrangement of distance, motion, and time. That is why the study of rogue planets remains incomplete. Astronomy knows that worlds can exist without stars. It knows several ways they can form or be expelled. It has detected planetary mass objects moving alone and brief lensing events consistent with free-floating planets. What remains uncertain is the full population. How many exist at each mass? How many formed in disks? How many formed directly from collapsing gas? How many carry moons? How many preserve atmospheres or oceans? How many have traveled alone since the earliest stages of their systems? These questions will not be answered by one observation. They will be answered gradually through repeated surveys, longer records, sharper instruments, and better comparisons between theory and what the sky reveals. Each detection will add one point to a larger map. A short brightening in a crowded star field, a faint infrared object moving between exposures, a spectrum shaped by clouds above a world with no sun, a gravitational event lasting only a few hours. From such small signals, astronomers will continue building the history of planets that left no visible trail. The importance of these worlds does not depend on whether they resemble Earth. They matter because they reveal how planetary systems change. They show that formation does not always end in stable orbits. They preserve the outcomes that mature systems no longer display. A finished planetary system is only one possible arrangement. Around young stars, gravity tests many others. Some worlds remain. Some collide. Some migrate. Some fall inward. Some cross the final boundary and never return. The rogue planet is the continuation of that last path. It begins among dust and gas, in the same bright environments where ordinary planets are born. It grows through the same collisions. It gathers the same elements made inside earlier generations of stars. Then one encounter changes its orbit. The planet moves outward. The parent sun becomes one light among many. Surface warmth fades, while the interior continues releasing an older heat. Ice spreads, atmospheres change, moons, if they remain, keep circling. The world enters the galaxy alone, but never outside gravity. It follows the Milky Way through epochs too long to measure by seasons. It passes stars without joining them. It crosses clouds without stopping. It carries the materials of one planetary system through regions that system will never reach. And somewhere along its path, for a few hours, its gravity may bend the light of a distant star toward Earth. A detector records the brightening. Astronomers recognize the curve. The event fades, leaving no image of a surface, no map of an ocean, and no name for the star that once held the planet. Only the evidence that a world passed there. Then the background star returns to its earlier brightness, and the planet continues beyond the light.